Hi everyone. Today I will discuss about numerical integration. So first of all, we want to know what is integration. Okay. So consider a function which is a function of a single variable f of x. We can plot the function. The variable is along the horizontal axis and the function in the vertical axis. And suppose this is the curve f of x. This black one is the graph of f of x. And a definite integral from a to b f of x dx. What is the geometrical meaning? It is actually the area under this graph f of x from a to b. That is the area between x-axis and f of x from the limits a to b. This area, shaded area, is the value of integral. Okay, so the meaning of definite integral a to b f of x dx is area under f of x from a to b. And if f of x has some specific forms like x raised to n, we have the answer x raised to n plus 1 by n plus 1. If it is sin x, we have the answer minus cos x. If it is cos x, it will be sin x, and so on. So for very few functions, we know how to do the integral. And that is known as analytic methods, analytic integration. But if this f of x has some complicated form, it will be very difficult to find the answer of integration. In such cases, we can use numerical methods. And today we will discuss 3 numerical techniques to find the value of integral. And the idea behind all the 3 methods is identical. The only difference is in the polynomial, in the degree of polynomial that we are choosing. And the basic idea is replace this function f of x using a polynomial function. If you are choosing a first degree polynomial, that is a linear function like a1x plus a0. Here the variable x is in first power. So this is a linear function, or it is a function of first degree. So it is a polynomial of first degree. If you approximate f of x using this function, and if you calculate this value of integral, that method is known as trapezoidal rule. Why this name I will explain. And if you choose a second degree polynomial in order to approximate the original function like a2x square plus a1x plus a0, then that method is known as Simpsons 1/3 method. If you choose a third degree polynomial in order to approximate the original function like a3x cube plus a2x square plus a1x plus a0, then that method is known as Simpsons 3/8 method. So in all these methods, we are going to replace the original function f of x with simpler functions like a first degree polynomial, second degree polynomial, third degree polynomial, and so on. Okay, this is the idea. Now I will explain one by one. First we will consider the trapezoidal rule. Here original function f of x will be replaced with a first degree polynomial which has the standard form a1x plus a0. Okay, what is the geometrical meaning? Here you have the variable axis x, you have this function axis here f of x, and the original function is this black one, this somewhat quadratic nature, this function, and the original answer for this integral is the area under this graph. But in trapezoidal rule, what we are going to do is we will approximate this function, or we will replace this function with a linear function which passes through the 2 endpoints. That is, this straight line should pass through this point, or should have the same value as that of f of x at x equal to a as well as at x equal to b. Okay, so that is the condition. This straight line and the original curve should have the same value at both endpoints. Then if you replace this f of x with this first degree polynomial a1x plus a0 dx, this integral you can evaluate because you know the value of x raised to n dx as x raised to n plus 1 by n plus 1. So if you apply that here, a1 is a constant, you can take it outside. X dx becomes x square by 2. The answer of x integral x dx is x square by 2 and the limit is a to b. Similarly, in the second term a0 will come outside. Integral dx is x from a to b. Applying limits, you will get it as a1 by 2 into b square minus a square plus a0 into b minus a. Upper limit minus lower limit. So this integral is still arbitrary because there are two constants a1 and a0. This a and b, you already know what is the limits of integration, that will be given in a question. But a1 and a0 are completely arbitrary. So we have to find these two unknowns. In order to find these two unknowns, we should know two equations that contains these unknowns. In order to get that equation, we will use this first assumption. The linear straight line, this function f1x and this original function f of x both matches at endpoints. That means at x equal to a, f1 of a should be equal to f of a. That is a1 into a. f1x is a1x plus a0. So f1a is a1a plus a0. That should be equal to f of a. Similarly, at the other end, a1b plus a0 equal to f of b. If you subtract these two, you will get a1 into b minus a is f of b minus f of a, or a1 is 1 by b minus a into f of b minus f of a. This is the value of a1. Substitute that value of a1 in one of the equation, then 1 by b minus a into f of b minus f of a into a plus a0 equal to f of a. That means a0 equal to, this a0 equal to, here you have in the right hand side you have an f of a, and then from left hand side you will have an a by b minus a f of a by b minus a f of a minus a by b minus a f of b. So you will get a0 as b f of a minus a f of b divided by b minus a. And a1 we already have this value 1 by b minus a into f of b minus f of a. Okay, so the required integral I approximately half into b square minus a square into a1. a1 it is 1 by b minus a f of b minus f of a plus a0 into b minus a. So b minus a into a0 is b f of a minus a f of b divided by b minus a. This b minus a and this b minus a will get cancelled. B square minus a square is b minus a into b plus a. So one of the b minus a will cancel. So what the remaining is 1 by 2 into b f of b. Here it is b plus a, b f of b minus b f of a plus a f of b minus a f of a. Okay, and in the second time you have b f of a minus a f of b. Therefore I approximately equal to here you have a b f of a and here you have a minus b f of a. So both together you will have b by 2 f of a. So this term is over. And here you have a minus a f of b. Here you have plus a by 2 f of b. So that together, this term and this term together, you can write it as minus a by 2 f of b. And here you have plus b by 2 f of b. and here you have a minus a by 2 f of a. Therefore, I approximately equal to b minus a by 2 into f of a plus b minus a by 2 into f of b. Okay, that is, it is approximately b minus a by 2 into f of a plus f of b. This is the answer for integral. I approximately equal to b minus a by 2 f of a plus f of b. So this is the answer. Now, why it is known as trapezoidal rule? Because this, consider this specific example, or in the first figure you can see that this shape, this is a four-sided shape, and the two sides are parallel. Okay, in mathematics, if you have a shape with four sides in which two sides are parallel, it is known as trapezoid. And for trapezoid, the standard equation for finding area is sum of parallel sides. Here your parallel side, the height is f of a and this height is f of b. So sum of parallel sides, f of a plus f of b, into the distance between parallel sides. The distance between parallel sides is b minus a, divided by 2. Okay, that is the equation of area of trapezoid. Half into sum of parallel sides into spacing between parallel sides. So that is why it is known as trapezoidal rule, because this is actually the area of a trapezium. Okay, so I approximately equal to b minus a by 2 into f of a plus f of b. This is the answer of numerical integration. Consider this specific example. You want to find this definite integral 0 to 2 x square dx. X square is a quadratic function, it's a polynomial. So I am plotting only the right hand side from 0 to 2. It will be something like this black one. Okay, this black line. This is f of x equal to x square. This is f of x equal to x square. What is the actual value of integral? Because this is a very simple function, you know how to evaluate this integral. X square dx, answer is x cube by 3. If you put the limits 0 to 2, you will get it as 2 cube by 3, that is 8 by 3, and it is 2.67. If you use trapezoidal rule, you have to use this equation. B is here upper limit 2, a is the lower limit 0, f of a, this function value evaluated at a lower limit because 0 square is 0, and f of b, the function value evaluated at upper limit 2 square. Okay, so 2 square is 4. 2 and 2 will cancel. The final answer is 4. So there is a large error. What is the error value? Error is 4 minus 2.67. It is 1.33. What is error percentage? It is 1.33 divided by original value 2.67. So it is 50%. 50% error. So what is the problem here? The original curve is a quadratic one. Area under this graph is this green portion. In trapezoidal rule, what we are doing is we are fitting a straight line between the endpoints. So from 0 to 2, and that straight line should pass through the function curve. At both endpoints, function curve and this straight line should match. That is the idea. Here, if you calculate the area under this straight line segment, then that will be this area of triangle. Definitely the error portion is this extra, this red color region. The area of this red color region is 1.33. Plus this 2.67, that will give you the total 4. So in trapezoidal rule, the final answer need not be the exact value. In all numerical methods, you will get an answer which is close to the true value. But here that is very far because the error is 50%. Okay, so there is always some disadvantages in any method. Okay, but we will try to find a solution to get a better answer. So consider this function, integral 1 to 5 x plus 1 dx. 1 to 5 x plus 1 dx. True value is, this is also a familiar function, x dx x square by 2, integral dx x. If you are putting the limits, you will get it as 12 plus 4, 16. In trapezoidal rule, half into upper limit 5 minus lower limit 1, f of x evaluated at 5, it is 5 plus 1, f of x evaluated at 1, it is 1 plus 1. Final answer is 16. So error is 0. Why here error is 0? Because the original function itself is a linear one, and in trapezoidal rule we will fit a straight line connecting the initial point and final point. So both the f of x as well as this is f of x and the approximating polynomial, both are same. So both are having the same area. Therefore error is 0. That means if your original function is linear, in trapezoidal rule you will get exactly same answer that you obtain when you use analytical methods. Okay, in numerical method and in analytic method you will get the same result if your function is a linear one. Okay, and we can show that the error in trapezoidal rule is proportional to second derivative of the given function. If the function is a linear one, second derivative will be 0 and error will be 0. If the function is quadratic, there will be some error. As you seen in this example, if the function is quadratic, there will be error. But if the function is linear, there will not be any error. Okay. Consider this function. I is equal to integral 0 to pi sin x dx. The given function is sin x. If you plot sin x from 0 to pi, that will be something like this, sin x. And the true value of integral is minus cos x from 0 to pi, answer is 2. If you apply trapezoidal rule, you have to draw a straight line from 0 to pi. So that straight line will be parallel to x-axis, or it is along the x-axis. Then area under this graph, this red line and x-axis, area between this red line and x-axis is 0. So trapezoidal answer will be 0. Half into upper limit minus lower limit plus function evaluated at upper limit plus function evaluated at lower limit. Sin pi is 0, sin 0 is 0. So trapezoidal rule will give you an answer 0. Error is 2. So 100% error. From this geometrical plot, we can see why that error happens. And you can also think of a solution. How can we find a better value using trapezoidal rule? The idea is, instead of fitting a single straight line between these two limits, you first fit a straight line from 0 to pi by 2, then fit a straight line from pi by 2 to pi. Okay, then you can evaluate this area. So from 0 to pi by 2, area under this straight line is this one. From pi by 2 to pi, area is this one. Then error will get reduced. We can look at what is the error in this case. 0 to pi by 2 and pi by 2 to pi. In the limit 0 to pi by 2, you can call that integral as I1. From pi by 2 to pi, call it as I2. So for I1, upper limit is pi by 2, lower limit is 0. So half into upper limit minus lower limit, b minus a, into sine of pi by 2. Function value evaluated at upper limit plus function value evaluated at lower limit. Plus for the second trapezoid, half into upper limit is pi, lower limit is pi by 2, sine pi plus sine pi by 2. Sine pi by 2 is 1, sine 0 is 0, so it is pi by 4. Here also sine pi is 0, sine pi by 2 is 1, pi minus pi by 2 is pi by 2 into 2. This will give you pi by 4. Pi by 4 plus pi by 4, final answer is pi by 2 and it is 1.57. Error is 0.43. Exact value is 2 and you are reaching closer 1.57. From 0 you reach to 1.57. Error is almost 25%. In order to further reduce the error, what is the idea? You further split this region, okay, into say 4, that is you are fitting 4 straight lines. First from 0 to pi by 4, then from pi by 4 to pi by, these vertical lines are not the straight lines fitted. Straight lines fitted are these ones, okay, these red ones. 0 to pi by 4 a straight line, pi by 4 to pi by 2 another straight line, pi by 4, pi by 2 to 3 pi by 4 another one, 3 pi by 4 to pi another one. Then you can see that the area is almost covered, okay. This is the area under this, okay. If you take 4 segments, you can include this much area, and error will be very small, we can calculate. So there are 4 integrals, I1, I2, I3, I4. There are 4 trapezoids, okay, 1, 2, 3, 4. In the first case, half into upper limit is pi by 4, lower limit is 0, sine pi by 4 plus sine 0. Second case, half into upper limit pi by 2, lower limit pi by 4. Third case, half into upper limit 3 pi by 4, lower limit pi by 2. Fourth case, upper limit pi, lower limit 3 pi by 4. And exactly the same equations for all the cases. You can see that the answer is 0.277, I1, I2 is 0.670, I3 is 0.670, I4 is 0.277. Final answer is 1.89. So error is 0.11 only. Okay, so error gets reduced. If you divide it into 8 parts or 6 or 5, anyone, you can divide it into any number of parts, okay, no restriction, okay. If you can divide it into 9 or 12 or 14 or 15 or 100, if you increase the number of segments, the error will get reduced. And with this idea, we can look at multiple segment trapezoidal rule. Suppose you want to evaluate an integral I from x0 to xn, the lower limit I denoted it as x0, upper limit is xn, f of x dx. And suppose the curve is something like this black one. By fitting a single straight line, error will be very large. From starting point to ending point, if you fit a straight line, error will be very large. Then our idea is fit a number of straight lines. One from x0 to x1, the second one from x1 to x2, then from x2 to x3 and so on. Final one from xn minus 1 to xn. Then the first one you call it as I1, second one I2 and so on. For the first one, upper limit is x1, lower limit is x0. So x1 minus x0 by 2 into function value evaluated at x0 and x1. Plus for the second trapezoid, third trapezoid, and for this last trapezoid. And if you are dividing this total interval into equal intervals, okay, n segments, each having the same width, and suppose that width is h. That is h is xn minus x0 divided by n, where n is the total number of segments. Then this x1 minus x0 is h, x2 minus x1 is h, xn minus x1 minus 1 is h. All these quantities are h, and you can take h by 2 outside. Then this f of x0 comes only one time, and f of xn also only one time. F of x1, here you have an f of x1, and here also you have an f of x1, because x1 is a part of two trapezoids. x1 is part of this first trapezoid as well as the second trapezoid, so it will come twice. x2 is a part of this trapezoid and this trapezoid, it will come twice. But x0 and xn are part of single trapezoid. Therefore, it will come only once, f of x0, f of xn. All other in between points, I equal to 1 to n minus 1, will come twice. So this is a multiple segment trapezoidal rule. I approximately equal to h by 2 into f of x0 plus 2 into sigma I equal to 1 to n minus 1, f of xi plus f of xn. Okay, this is multiple segment trapezoidal rule. Here we can look at the same problem we discussed with a single segment, integral 0 to 2 x square dx using two segment trapezoidal rule. Two segment means n equal to 2, so you can calculate h. H is upper limit minus lower limit divided by number of segments, so it is 2 by 2, it is 1. Once you have h, you have to write this total interval 0 to 2 with the gap of h. So you have 0, 1, 2. Denote these 3 points x0, x1, x2. Equation is I equal to h by 2 into f of x0 plus the center point, it will come twice, 2 f of x1 plus f of x2. F of x0, here you have f of x square, f of x0, x0 is actually 0, so it is 0 square. F of x1, f of x is x square, x1 is 1, so 1 square. But here you have 2 f of x1, so 1 square is 1, 2 into 1, 1, 2 into 1, 2. And f of x2, x2 is 2, f of x is x square, so 2 square is 4. 4 plus 2, 6, 6 by 2, 3. The actual value, true value of this integral is 2.67. Single segment you obtained a value of 4, but now with the 2 segment you obtained a value of 3. So error is only 12%. Earlier error was 50%. Okay, so error gets reduced by using 2 segment trapezoidal rule. So by increasing the number of segments, you can increase the accuracy of the result. And since these are actually done by computer, no issue. If you take any number of segments, the answer will come very quickly. Okay, so all these are actually numerical methods. Okay, we have to write a program, then feed it into the computer, and if you just give the input as n is equal to say 100, lower limit, upper limit, f of x and n. These are the 4 inputs you have to given to the computer. Okay, lower limit, upper limit, function and the number of segments. And you can type any number of segments, n is equal to 100 or n is equal to 1000. Okay, then you will get results of better accuracy. So this is the idea behind trapezoidal rule. Okay, the actual function, if you don't know how to evaluate analytically, then you just approximate that function with a linear polynomial or first degree polynomial. That method is known as trapezoidal rule. But if you fit a single straight line from the initial point to final point, you will have a very large error. Then you can split that interval to a large number of segments and fit a smaller straight lines from the initial point to final point, and you will get a answer with a greater accuracy. Okay, now Simpsons 1/3 rule. The only difference is here you are going to approximate this function f of x with a second degree polynomial, a2x square plus a1x plus a0, integral a to b. Again, this function you know how to integrate. A2 into x square dx integral is x cube by 3. By putting limits you will get b cube minus a cube by 3 plus a1 into x dx x square by 2, putting limits b square minus a square by 2 plus a0 into integral dx x, putting limits b minus a. Here you have 3 unknowns, a0, a1, a2. So we require 3 conditions in order to evaluate the 3 unknowns. For that we require we are assuming that this f1x and f of x matches at 3 points. Okay, not f1x, f2x. Your approximated polynomial f2x and original function f of x, this black curve and this red curve, matches at 3 points. One at the initial point, one at the final point, one at the midpoint. That is our assumption. Okay, by taking this assumption, we are going to derive the final expression. So that final expression is valid only when this f2x and f of x matches at 3 points. Initial point, center point, final point. Okay, that is our assumption in this case. So you can take f2 of a as f of a, f2 of a plus b by 2 as f of a plus b by 2, f2 of b as f of b. So you will get 3 equations. By solving that, you can find a2, a1 and a0. Substituting that value back into the equation, you will get I approximately equal to h by 3 into f of a plus 4 into f of a plus b by 2 plus f of b. Okay, that finding this a1, a2, a3 or a1, a2 and a0 involves some algebra. You can use Cramer's rule to find or to solve the system of 3 equations. Okay, and you can find how we arrive at this equation. Okay, you can do it as a homework. Now, what is the idea of this equation, or why this name Simpsons 1/3 rule? Due to this factor 1 by 3. Okay, due to this factor 1 by 3, it is known as 1/3 rule. And h is actually this width, not the entire width. The width or entire width you can take it as 2h. Okay, 2h. So h is this one. And f of a, value of function at a, f of a plus b by 2, value of function at this point, f of b, value of function at this point. Middle point, it will be multiplied with a 4. Okay, this is the expression that you will obtain if you substitute the value of a2, a1, a0 here. a2 is a1, a0 you can calculate using Cramer's rule by arguing that this function and polynomial should match at 3 points. You will get 3 equations, 3 linear equations. Solve it using Cramer's rule or something. You can find the constants, substitute back this in equation, then you will get this equation. Okay, that is the idea. Now, consider this equation I, integral 0 to 2 x square dx. Lower limit a0, upper limit b2. So the midpoint a plus b by 2 is 1. That means h is 1. Because h is the distance from lower limit to the midpoint. Number of segments, here it is 2. We will have 2 segments actually, and h value is 1. I is 1 by 3. H by 3, actual equation is h by 3, h is here 1. Plus f of a is 0. F of a means 0 square 0. 4 into f of b, not f of b, f of a plus b by 2. So it is f of 1, 4 into 1, 1, plus f of b. B is 2, so f of b is 2 square 4. Answer is 8 by 3. True value is also 8 by 3, so error is 0. Why? Because the original function is quadratic and we are approximating the function with the quadratic polynomial. So both will give you the same result. What about if you evaluate 0 to 2 x raised to 4 dx? True value is 6.4. X raised to 5 by 5, 2 raised to 5 by 5, 32 by 5, 6.4. Using Simpsons 1/3 rule, you will get 6.67. These are very easy. H is again 1 by 3 into function value evaluated at lower limit, midpoint and upper limit. You will get 20 by 3, 6.67. So there is error. Okay, so if you are considering a polynomial of the order of 4, then you will have error. What about x raised to 3? If you take integral 0 to 2x cube dx, true value is x raised to 4 by 4, from 0 to 2, answer 4. Simpsons rule will give you a result I equal to h by 3 into f of a plus 4 into f of a plus b by 2 plus f of b. That will give you 4. Error is 0. So we are in Simpsons 1/3 rule, we are approximating the functions with a quadratic polynomial. Here you have a cubic polynomial. Even then the error is 0. Okay, and if you derive the error in Simpsons 1/3 rule, you can see that it is proportional to fourth power of the fourth derivative, not fourth power, fourth derivative of the function. So even if it is a cubic polynomial, fourth derivative will be 0. Okay, you can also have x cube plus 3x square plus 2x plus 1, something like that. Then also your fourth derivative will be 0 and you will get the same result or you will get the true value of integral if you use Simpsons 1/3 rule. So error in Simpsons 1/3 rule is proportional to fourth derivative of function. If the fourth derivative of a function vanishes, then error in Simpsons 1/3 rule will be 0. If a second derivative of a function vanishes, then the error in trapezoidal rule will be 0. Now, in order to increase the accuracy, as we did in the case of trapezoidal rule, here also you can fit more polynomials, more second degree polynomials. Then you will get a multiple segment Simpsons 1/3 rule. But in order to fit one polynomial, it should pass through 3 points, the endpoints and midpoint. And in here, one segment means the segment from initial point to midpoint. If you are thinking that way, the total number of segments should always be even. Then only you can fit a polynomial between two, the next polynomial between the next two. Okay, so if you end up with an odd one, you cannot, it is not possible to fit a polynomial. So the condition for getting result from multiple segment Simpsons 1/3 rule is number of segments is even. Either 2 or 4 like this. The next possibility is 6 and the next possibility is 8 and so on. Okay, in order to fit a quadratic one, you need 2 segments like this, each having a width h, 2 segments. Then for the next polynomial, 2 segments. For the next polynomials, 2 segments. Okay, so if you are end up with a single segment, then it is not possible to fit that polynomial. So for multiple segment trapezoidal rule, number of segments should be even. Suppose you have even number of segments, then what is the next procedure? For the first 2 segments, you write I1. For the next 3 and 4 segments, you write I2 and so on. For I1, initial point is x0, midpoint is x1, if this point is x2. So h by 3 into f of x0 into midpoint, it will come 4 times plus f of x2. And for the second one, initial point is x2, midpoint is x3, final point is x4 plus etc. and so on. Therefore, we can see that initial point will come only once, final point will come only once, and this 1, 3, 5 etc. all those will come 4 times. I equal to 1, 3, 5 etc. up to n minus 1. All this will come 4 times. Then what about this f of x2? Here and here. So it is 2. F of x4, it will be here and in the next one also. So this 2, 4, 6, 8 etc. up to n minus 2, it will come twice. So this is multiple segment Simpsons 1/3 rule, and the condition is n should be even, and h is width of one segment, and that is actually this width, not the width of one polynomial fit. Okay, it is half of that. So h is width of segment, and for Simpsons 1/3 rule, the number of segments should be even. That is the condition. I hope it is clear. Okay, so this is the idea. Now I will comment on error. Error in multiple segment trapezoidal rule proportional to 2 factors. One is second derivative of the function evaluated at an arbitrary point. Why this point is an arbitrary point? If you know exactly this point, then it is possible to find the exact error by evaluating the second derivative and by dividing with n square. Then by adding that exact error to the approximate value of integral, you can find the true value. Okay, it doesn't make any sense. That is, if you have a complicated function, then analytic integration is not possible. It is not possible to find the true value of the integral. Then we can think of numerical integration. Numerical integration will give you an approximate result that is not a true value. But along with that approximate result, if you can calculate the true error, then that the sum of both will give you the exact result. Okay, but that is senseless, because true value, whenever you have a difficulty to find true value, you are depending upon numerical integration. And in numerical integration, there is always some error bar. Okay, you cannot find the true value. In the case of error, you can find an approximate measure of error, but never you find the true error. Okay, it is not possible to find the true error in any case. So this is theta is an arbitrary point. It is between x0 and xn, but it is not an or it is an arbitrary point. Okay, so error is proportional to second derivative. That is the first point in the case of multiple segment trapezoidal rule. Second, error is inversely proportional to square of the number of segments. As number of segment increases, error will get decrease. In the case of Simpsons 1/3 rule, error is proportional to fourth derivative of function, again evaluated at an arbitrary point, and it is inversely proportional to fourth power of number of segments. Okay, so that is all about the numerical integration. And now if you have Simpsons 3 by 8 rule, what is Simpsons 3 by 8 rule? Here you are approximating this f of x with a cubic polynomial. Then when you evaluate this, or when you replace the original function with this function a3x cube plus a2x square plus a1x plus a0 into dx, you can easily evaluate this integral. I approximately equal to a3 by 4 into xn raised to 4 minus x0 raised to 4 plus a2 by 3 into xn cube minus x0 cube plus a1 by 2 into xn square minus x0 square plus a0 into xn minus x0. If you find a3, a2, a1, a0, you can find the value of integral. But how can we find a3, a2, a1, a0? We need four conditions. So idea is demanding that the function, original function and the approximated cubic polynomial should match at 4 points. That is, if your original function is something like this is initial point x0 and this is initial final point xn. Divide this into 3 segments. Here you have x1, here you have x2, and argue that the cubic polynomial should pass through these 4 points: x0, x1, x2 and xn. Okay. Or in the case of if you have only 3 segments, then it will be x0, x1, x2, x3. If you equate the function value and this cubic polynomial value at these 4 points, you will get 4 equations. 4 linear equations you can solve using Cramer's rule and find a3, a2, a1 and a0. Substituting back the values, you will get I approximately equal to 3h by 8. That is why it is known as 3 by 8 rule. F of x0 one time, 3 into f of x1 plus 3 into f of x2 plus f of x3. This is the general expression. Okay. F of x0 plus 3 into f of x1 plus 3 into f of x2 plus f of x3. This is Simpsons 3 by 8 rule. Again, if you take a multiple segment rule, then what will be the condition? Number of segments should be, if you are taking multiple segment rule, what is the condition? Number of segments should be multiple of 3. Because when you fit a cubic, you should have 3 segments. This is the width of one segment, h. So total width is 3h. In order to fit the next cubic polynomial, again you need 3 segments. So whenever you apply multiple segment Simpsons 3 by 8 rule, the number of segments should be multiple of 3. Okay, that's the condition. Simpsons 1/3 rule, number of segments should be multiple of 2. And in trapezoidal rule, no such restrictions. Any number of segments is possible. And in the case of Simpsons 3 by 8 rule, also the error is proportional to fourth power of fourth derivative of the function evaluated at an arbitrary point, and it is proportional to n raised to 4 also, inversely proportional to n raised to 4. As the number of segments increases, the error decreases as 1 by n raised to 4. The proportionality constant is such that Simpsons 1/3 rule is more correct compared to Simpsons 3 by 8 rule. Okay, so in most cases we are using Simpsons 1/3 rule. So that's it. So this is the idea of numerical integration. Okay, replace or approximate the original function with the polynomials. It can be a first degree polynomial, or it can be a second degree polynomial, or it can be a third degree polynomial, and so on. Okay, so thank you everyone.